Hello, I'm Daniel Lowen, and I'm going to talk to you about entropy. Entropy, particularly how it relates to computers. So, one of the first things, what is entropy exactly? And it's basically randomness at a very simple level. And randomness happens all throughout our lives. Random events constantly occur. And that would be entropy. But what's interesting about life, or about computers in particular, is computers kind of suck at random numbers. They really aren't capable of generating randomness. You feed it an input, it gives you the same output every time. Generally speaking, if it is erroring out or doing something weird, it's somebody made a mistake in the logic of the computer itself. Very rarely do bits get flipped or something along those lines. There are a handful of exceptions, but entropy does not happen on computers. If you ask a computer, hey, I need you to generate me a random number, it's not truly random, and we'll talk about that. So, can computers generate random numbers? Short answer is no. Long answer is, well, not without some help. It can look pretty darn random, and it can be pretty darn good. But it's never going to be perfect. So we call this a pseudo random number generator, or a PRNG. Here's a funny little comic. It just says Tour of Accounting. This is from Dilbert by Scott Adams. Over here we have our random number generator. It's saying 99999 over and over again. And this guy says, are you sure that's really random? And this little monster dude says, that's the problem with randomness. You can never be too sure. It could say 999 over and over and over again, and guess what? That could have actually just been a random event. Highly unlikely, but it is just pointing out that it is kind of difficult. So why would we care about this? Why is it so bad that we can't generate random numbers very well? Well, online casinos care. A lot of those slot machines and so forth are now digitally driven, and they care very much about the quality of those random numbers and making sure that it is reasonably random, and of course they, win their money, right? Cryptography uses random numbers a lot. So SSL, what you use to go to a website, every time you go, there is an exchange of what's called a session key, it's a shared key that both you, the client, and the server you're connecting to need to share throughout that entire session. It's randomly generated, and then it's securely shared using asymmetric encryption, but that needs to be a genuinely good random number. If it's not a good random number, it won't work. Initialization vectors are another thing. Symmetric encryption also uses a thing called an IV, or initialization vector. Those need to be random in order for it to start encrypting data. Private keys, we talked about asymmetric encryption. Those are private keys. They need to be randomly generated when they're first created. They're not created very often, but they need to be very random. A nonce is a number once. It's kind of like a session key. Also, websites, when you authenticate to google.com, you type in your username, you type in your password. That's another example of a session key. What is actually happening is, if you authenticate correctly, Google will send you a session key that you'll store in a cookie. And that's how you authenticate from there on out to every website. And that is a randomly generated value. If these values are guessable, then the entire security of all these different products will completely fall apart. And this actually has happened in the past. And we'll talk about some examples of how that has occurred. Here's another funny XKCD for anyone that's ever programmed. It just says int get random number, and it always returns 4. Ha ha ha. Chosen by a fair dice roll, guaranteed to be random. Of course, you call it every time, it's going to be 4 again. So there's terminology here. Pseudo-random number generator. It is what computers are. They are not true random number generators. A CSPRNG is a cryptographically secure pseudo-random number generator. It's basically a PRNG, but a lot better. It's designed to be a lot less guessable. Generally speaking, there's a lot more load on the system with CSPRNGs, so you don't want to necessarily use them unless you need it. But when you're generating those session keys, those nonces, they're very important. A true random number generator, computers aren't this, but we will show you how people have come up with really cool ways to do that as well. With some outside help, we can actually become a true random number generator. And finally, entropy. We've already sort of mentioned that. Entropies usually collect randomness in a pool. So throughout your normal day-to-day operation, it's collecting randomness. So for example, when you're shaking your mouse, it's actually recording that because that's pretty darn random. I mean, obviously you're doing some things, but exactly how you move that mouse, that's going to be pretty random. They'll look at things like timing of packets and timing of keystrokes on your keyboard. And all that builds as randomness into the entropy pool so that when it needs randomness, it will pull from that entropy pool. And that's how most operating systems collect their randomness. What is a good random number generator? Each value is statistically independent of one another. So example, given a number, it's not more likely that the next number will be a specific number. It's every time you're grabbing a number, it's completely random. If you've got, there's no sort of pattern in there. Uniformly distributed. So if you generate 100 numbers from 1 to 10, you should have about 10% of each number. The more numbers you generate, the closer to 10% it should get. It's just, that is a good random number generator. For example, you generate 100 random numbers and you ended up with 42s, and you do it again, you end up with 42s again. It's probably not a very good random number generator. Finally, unpredictable. If you have a series of numbers, you shouldn't be able to figure out both past and future numbers. Each number is independent and completely random. Here's a good example. What they did was they sort of mapped out random numbers. On the left-hand side is good. You can see it looks pretty random. There doesn't seem to be a lot of patterns. PHP on Windows, I believe this has been fixed, but notice how there's some pretty clear patterns in there. That is a bad random number generator. Not considered good. So some sources I've already kind of talked about: I/O devices, mouse, keyboard timings, interrupts from disk, timing of network packets, and so forth. So some problems. One of the problems is servers often don't have keyboards and mice hooked up to them. There's not really a user at a server much. Disk and network I/O on some servers aren't always very prevalent, right? Some servers don't receive a lot of packets. They might not receive a lot of disk I/O. It's not it's not gaining entropy into that pool. Other issues. Entropy is known to be poor on systems when they first boot up. They haven't built that pool up, so when you first turn on a computer, they actually aren't as random on some systems, and we'll talk about how some operating systems have tried to solve this problem. Another interesting tidbit is virtual machines, which are very prevalent. We're all pushing everything to the cloud. Everyone's virtualizing everything. Generally speaking, virtual machines do not collect enough entropy. They don't do random numbers nearly as fast as a physical machine. And we'll talk about why that is and what is being done to fix that. Finally, random number generation can be blocking. So what does that mean? So in Linux, for example, Linux is, to my knowledge, the only blocking OS for random number generators. When that pool, it builds up. When you grab a number, it pulls off that number and then is never used again. It throws it away. If that pool gets completely depleted and an application calls it, that application hangs until that pool has been added to. that isn't a very good sign, right? That's not necessarily a good thing. If your applications are hanging, if users can't access what they need to access, that's not necessarily a good thing. So that is what we mean by random number generation could be blocking. Ideally, we don't want that. So we'll talk about ways that they've sort of come to do that. This is a Linux specific thing. Various versions of Unix do random and urandom differently. A lot more of them now have decided that, we'll talk. So Linux random is blocking. So /dev/random is a blocking. When that pool gets depleted, it ends, right? So when the pool is exhausted, the application freezes until there's more randomness added into the entropy pool. Unlimited random, or urandom, falls back on using time for generating random numbers. So if it depletes that entropy pool, it starts using time mixed in with some previous values. It's not very random. So urandom might be good if you're making, like, say, a video game where randomness isn't super important. You're not like a casino losing potentially millions of dollars, right? And you don't want the application to block. You don't want the whole game to freeze on a user because, well, they ran out of randomness. Dev random is considered secure. Some Unix operating systems no longer draw a distinction. If you pull from dev random and dev urandom, they end up pulling from the same source. And we'll talk about what they've done to sort of accommodate that. So one example, and there's a lot of them out there, is used by various BSD systems, including Opera OS X from Apple. They're still collecting entropy, but when they do, they encrypt the data using a stream cipher. So that uses a symmetric key. And if you remember, when we talk about stream ciphers need to look random. So when you're sending out a data across any symmetric encryption algorithm, it should be indistinguishable from randomness. You shouldn't be able to tell what is random and what is not. Old random numbers are fed back into the new random numbers, so it's taking the key and periodically XORing it, which is what they're showing, and sending it out, so it's constantly using. If you run out of random numbers, they fall back on time again, but they're still being mixed in with old randomly generated numbers. It never blocks, and it's able to produce a pretty decent amount of random numbers. So that's one solution. Here's an interesting graph, and I really enjoy this graph because this is showing the entropy pool in a virtual machine on the right-hand side versus a physical machine. What we can see here, virtual machines do not gain as much entropy, whereas the physical machine is gaining significantly more entropy. The pool is kept full a lot more often. And we'll see how a lot of newer manufacturers, a lot of the new OSs handle this, and it's becoming a bigger thing. So our solution is to borrow from the host. So Red Hat 7 in particular has a service called VirtIO that with certain hypervisors, it is able to pull random numbers from the physical host. So when a VM needs more randomness, it's able to go in and it's able to pull the random numbers out of it from the physical host itself, from that operating system. It's a good way of doing it, and we'll talk about next hardware random number generators, which is Intel and other more modern processor vendors have included. These processors are able to generate a significant amount of entropy, which really helps us out and really keeps that pool completely full. Now, when you combine these two, it's very, very powerful. So, another problem we said is on startup, systems have poor entropy, and this has been shown. For example, that if you generate a random private key at the beginning of startup, it's actually going to be a lot less random than if you were to let the system go for an hour or so. So people have come up with ways of fixing this problem. So the one would be an entropy broker. So the idea behind the entropy broker was we have a server and we keep it running somewhere on our network, and it's constantly generating entropy. And whenever a system boots up, it says, hey, system, you're always running, you're always building entropy. I need 4K of entropy. And that entropy broker would then give it a slice of its randomness, of its entropy, just to get that new system that just turned on started. Another probably more or less complex one is just save before you shut down. When you shut down a system nicely, save what was in your random entropy pool before shutting it down, and then use it next time. So operating systems do that as well to deal with the startup problem. Oops. Another example, and I'll include links to this. I think this link is wrong. What we can do is we can rely on outside sources into our system. One of the cool ones I have a video of, and it's on YouTube. Somebody came up with this really neat idea of basically dumping a bunch of dice, and then they have video cameras and they record the dice falling and how they fall, and they help build the entropy pool that way. Somebody else came up with a cool way of take a video camera, feed a video of a lava lamp into the computer, and use that to generate entropy. Others have done noise, so sound, video, radio, thermal noise as well. You can set up Wi-Fi cards and collect the wireless signals in your area, no matter if it's on your network or not. All sorts of different areas of random numbers. And generally, you don't use this as the only source of randomness. You just add it to that pool to keep adding entropy to it. Intel also came out with one in the Ivy Bridge. At Haswell, it's even gotten better. They collect entropy from thermal noise on the system. So the system, the processor has electrons that are being agitated because it's heating up, and they use that to then generate randomness that's fed into an AES encryption mechanism. It's capable of creating 3 gigabits per second of randomness, which is a lot of randomness. I mean, that is potentially a lot. People, including, just as sort of an example, Linux, there has been a petition to remove it from adding it to the entropy pool because they were afraid that it was potentially backdoored because nobody had the ability to audit it. So unlike software, which it's open source Linux, right? You can look at the software, you can try to understand how it's working. People didn't like the Intel one because, well, we can't look at it. We don't know how it's doing it. You can't directly use it with in virtual machines unless you have something like VirtIO, once again, where you're able to grab it from the physical host. And that's where VirtIO really is excellent to have. So some fails in random number generators. Debian, a number of years ago, accidentally commented out a line that collected entropy when you generated your SSH keys. So when the system comes up, it generates an SSH key. Those keys could easily be guessed. They really screwed up on that one. They later found it. They fixed it. And had to go out and say, look, if you generated keys from this time period to this time period, it is compromised. It is not a good key. Another one was dual EC DRBG, was an interesting one. It was added to NIST-FIPS, and a number of researchers said this has problems. We don't know what those problems are, but we're pretty confident that there's problems here. What was interesting is during the Snowden leaks, when Edward Snowden leaked information, it was leaked that NSA probably did this intentionally, and they were definitely aware of it. They paid RSA, which is a pretty prevalent company, and They paid RSA to make it a default. It later bit Juniper in the butt because they had a serious vulnerability that sort of stemmed from using this algorithm. Now theirs was slightly different and was supposed to have been fixed, but the way it worked is they got bit by it as well. Which a lot of people have said, look, this is the problem with adding backdoors to these types of products. What was even more interesting, around the time of the Snowden leaks, researchers actually figured out how it was done. Basically, what they proved was there was a random number that was part of the protocol. It was just random keys. It was a known key. And that's pretty common in encryption algorithms. Like AES has known numbers. They have like lookup tables and so forth. So it's not completely unheard of. But what was weird is no one knew how those numbers came up and why they picked those numbers. So what this researcher proved that is if you were in control of the numbers, you could use it as basically a one-way key to unlock any of the random numbers, and it would greatly reduce the strength of it. Just kind of another example. Crypto Shocker proved that 27,000 keys shared prime numbers. This should have never happened. So how do we test random numbers? And this is a cool demonstration I'm going to show you next. There's a tool called Die Harder, and basically what we're doing is we're generating lots of random numbers, and we're using statistics to figure out how good is this random number generator. It tests for uniformity, patterns, and so forth. It's also a good way to melt your computer. Your computer is going to work really hard and get really hot. So I'm going to show you an example of Die Harder next.